Alright, in this video we're going to go over single replacement and double replacement reactions. So for single replacement reactions, how you can identify those is when for your reactants you have one element and one compound reacting. Okay, so when you're trying to figure out what is switching with what, you need to pay attention to figure out whether the element is made out of a metal or a non-metal, okay? Because if you have a metallic element, it will switch with the metal or the ion with the positive charge in the compound. If you have a non-metallic element, it will switch places with the non-metal or with the ion with the negative charge in the compound. Okay, so I will write this out later on, but I did want to mention that. Okay, so for our template for this type of reaction, we have some compound AB reacting with some element C. And for this example, we will say that element C is metallic, or it likes to have it likes to create positively charged ions. So because in chemistry we typically write the positively charged ion first, okay, that's why I'm going to switch A and B. So we'll say for this example, we will say element C likes to form positively charged ions. So then what that means is A and C switch spots because you're just switching positive with positive. Okay, so that's why we get compound CB and then element A. Okay, but there, like I said, there are kind of two different scenarios, and it all depends on if your element in your reaction, or sorry, in your reactant side is either a metal or it likes to form ions with positive charges, or a non-metal. In other words, likes to form ions with negative charges. Okay, so we're going to get into the details of that just in a little bit here, but in general for single replacement reactions you could kind of think of it sort of like in this example here, you have a couple, like the compound that's already dancing together, and in this case element A is essentially just butting in and replacing partner B. So now we have a new compound, AC, and then we have element B all by itself. Okay, so that's one way of thinking of single replacement reactions and hopefully helping you to remember them. All right, now into the details here. So if you have an ionic compound reacting with a metal, so compound AB plus M for metal, okay, like I said, metals like to form positively charged ions. Okay, so that's why I'm gonna keep on sticking with like what type of charge of ions these elements like to form, instead of saying metal switches with metal, non-metal switches with non-metal, because sometimes things get a little bit more complicated than that. Okay, so elements with positive charges switch with other elements with positive charges. So for example here, let's say we have sodium fluoride. So sodium likes to have a +1 charge, fluoride likes to have a -1 charge. So +1, -1, that's going to equal 0, so this is already a balanced compound. I'm going to say that this is a solution of sodium fluoride, so this is going to be AQ, and we're going to say that it reacts with a piece of potassium metal. Okay, so since potassium metal, if we look at our periodic table, potassium is number 19, and it likes to have a +1 charge, which we can see right here. Okay, so we know that potassium likes to form ions with a positive charge. Sodium also likes to form ions with positive charges. So positive switches with positive. So in other words, potassium and sodium, they are going to switch spots. So we're going to get potassium fluoride plus sodium. Now sodium, when it's by itself, it is a solid. How I know that is because sodium is colored yellow, and according to our key on our periodic table, metallic solids are yellow. Okay, now for our compound, potassium fluoride, potassium likes to have a +1 charge, fluoride still likes to have a -1 charge, so that equals 0, so this compound's already balanced, but we do need to figure out what the state of this is. So since water is involved, because our sodium fluoride was a solution, so it was dissolved in water, we need to figure out, okay, is potassium fluoride soluble in water or not? So as a reminder, how you can figure out if an ionic compound is soluble in water or not is you can go to page 6 of your data booklet and you can look it up in your solubility table. Okay, so first things first, I need to find my anion, which is fluoride, and it says, okay, most things are soluble. But before I just go ahead and be like, yep, it's aqueous, I just want to check my list of exceptions here. Okay, so I don't see potassium down here, so that means, yeah, I can go with most. So it's very soluble, which means it is aqueous. All right, so each of the, actually, you know what, I'll leave that up. Each of the compounds are balanced, and actually this entire equation is already balanced as well, so I don't need to do anything. Okay. Now let's say we have an ionic compound reacting with a nonmetal. So nonmetals, they typically like to form ions that have negative charges. So I'm just going to keep this to negatives switch with negatives. Okay. So elements that form or like to form, maybe I should say that. Okay, so elements that like to form negative charges, they're going to switch. Okay, so for example here, let's say we have a lithium chloride solution. So lithium likes to have a +1 charge, chloride likes to have a -1 charge, so that's already balanced. And let's say it reacts with bromine. So bromine, it's part of Hofbrinkel, so it's a diatomic element. So that means when it's by itself, there's always two of them. And bromine, if you look at your periodic table here, so bromine is right here. It's colored red or pink, whatever you want to call that, which means that it is a liquid at room temperature. So I'm going to say this is a liquid. Okay, so since bromine is part of group 17, it likes to form ions with a -1 charge. So like I said, negatives are going to switch with negatives. So that means bromine and chlorine, they are going to be switching places here. But just as a heads up, whatever you do, the 2 doesn't necessarily come along for the ride with bromine. Okay? Just like the invisible 1 after chlorine doesn't necessarily come along for the ride. So remember, the reason in compounds, ionic compounds I should say, for the subscripts, it's just to balance the equation. Just because your bromine started out with a subscript 2 does not mean you're going to get LiBr2. Okay? You need to balance the compound with the subscripts. So let's write this out. All nice, neat, and pretty. Okay, so we have lithium bromide. Lithium likes to have a +1 charge. Bromide, likes to have a -1 charge. That's already balanced. Okay, I'll worry about the state of that in a second here. Chlorine, that's a diatomic element because it's part of Hofbrinkel, so I'm going to put a 2 there. And chlorine, when it's by itself, is a gas. How you can double check that is by looking at your periodic table, finding chlorine, and being like, okay, it is colored blue, and blue means that it is a gas. All right. Now back to lithium bromide. Oh, why isn't that erasing? There we go. Okay, so because water is involved in this reaction, because lithium chloride was aqueous, so it was dissolved in water, we do need to check the solubility of lithium bromide. So we need to go back to our handy dandy solubility table and figure that out. Okay, so I'm going to find my anion, or my ion with a negative charge first. So lithium bromide. Bromide is my anion. Most things are soluble with it, but I'm just going to double check my list of exceptions first. Lithium's not there, so yeah, it is soluble in water. Alrighty. Now we need to make double sure that everything is balanced. So what I mean by this is our skeleton equation right now. We need to make sure that we balance this equation. Okay, so I have 1 lithium coming in, 1 going out. That's balanced. But with chlorines, I have 1 coming in, 2 coming out. So I need to put a 2 coefficient here. I do not use subscripts to balance chemical equations. You only use coefficients to balance chemical equations. Subscripts are only to balance compounds. Coefficients are to balance entire equations. Okay, so that too, it didn't just affect the chlorine, it also affected the lithium. Okay, so I've got my chlorines are balanced, but now my lithiums are unbalanced. So I'm going to put a 2 right there. So we have 2 lithiums going in and coming out. And that 2 didn't just affect the lithium, it also affected the bromide. So I've got 2 bromines coming in, 2 coming out. So that is balanced. And that is all finished. All right, moving on to the other examples that we have here. Okay, just to give you lots of experience with this, just because this can be a bit challenging here. So we have sodium chloride. Solution, that means aqueous. Reacts with means that it's a plus sign. Potassium. Okay, so potassium is a solid. And because potassium likes to form positively charged ions, positive switches with positive. So sodium and potassium, they switch. So we're going to have potassium chloride. Potassium likes to have a positive 1 charge. Chloride likes to have a negative 1 charge. That equals 0. So we don't have to do crisscross applesauce. Plus, and we have sodium by itself. So sodium by itself is going to be a solid. Potassium chloride, let's see. So chloride, most things are soluble. Double check to make sure potassium isn't there. Yeah, we're good. So this is aqueous. Now, it looks like the entire equation is balanced as well, so I don't need any coefficients here. Moving on to calcium sulfate. So calcium sulfate. So if you're wondering how you remember what sulfate is, if it ends in ATE, it is going to be a polyatomic ion. And where we can find sulfate is right here. So that's SO4 2 minus. So 2 minus. And then calcium is right here. And it likes to have a 2 plus charge. So 2 minus 2, that's equal to 0. This is already balanced. Since it says it's a solution, this is aqueous. Reacts with means plus, and then iron. Iron is going to be a solid at room temperature. Okay, so iron likes to have ions that have positive charges. So remember, positive switches with positive. So that means iron and calcium are going to switch spots. And since calcium, I know that is going to be a solid at room temperature. Now for iron sulfate, the trick with iron is that it's a multivalent metal. We are going to assume that the ion that we're using is going to be the most common one. So that's going to be the first one listed. So the 3 plus is what we're using. So iron 3 plus. Sulfate likes to have a -2 charge. So because we know 3 minus 2 does not equal 0, we got to do crisscross applesauce. Okay? So because sulfate is a polyatomic ion, I'm going to put brackets around it because there's going to be more than just one. So we have a 3 and then a 2 right there. Okay, so that's balanced now. And now we need to check for state for iron 3 sulfate. So let's go to our solubility table. We're going to find our anion or our negative charged ion first. So sulfate is right here. Most things are soluble, but let's just make sure iron 3 plus isn't in our list of exceptions. Okay, I'm not seeing iron, so it is soluble. So I'm going to write this AQ. Maybe I'm going to move over this plus sign. There we go. All right. So we have our skeleton equation. Now let's move on to a balanced chemical equation. So I'm going to get rid of these arrows just to clean this up a little bit. We have 1 calcium coming in, 1 going out. 1 sulfate going in, but 3 sulfates coming out. Okay, so for polyatomic ions, especially with single replacement and double replacement reaction, sometimes it's actually easier to treat polyatomic ions as one unit to balance. Okay, so that's why I'm saying, okay, we have 1 sulfate here and 3 sulfates over here. So if I make the sulfates balance, so 3 coming in, 3 going out, but now our calciums aren't balanced. So the 3 didn't just affect sulfate, it also affected calcium. So we have 3 calciums coming in. Now we have 3 coming out. With iron, there's 1 coming in, but 2 coming out. So I'm going to go 2 right there. And now everything's balanced. All right, moving on here. We have potassium iodide solution. So potassium has a +1 charge, iodide has a -1 charge. That's balanced. Okay, reacts with bromine. So Hofbrinkel, it's a diatomic element, and it's liquid. Okay, bromine likes to form negative ions. Negative switches with negative. So bromine and iodide, they're switching spots. So we're going to get potassium bromide. So potassium has a +1 charge, bromide has a -1 charge. That's already balanced. Plus iodide, and Hofbrinkel iodide or iodine is a diatomic element. So there's 2 of them. Okay. So with iodine, it is right here. Since it's green, it's a non-metallic solid. Okay, so I know that's a solid, and I know I'm going to have to figure out the state of my other product, so I'll just switch right back there. So this is a solid. Okay, potassium bromide. Let's figure out where anion is. So bromide's right here. Most things are soluble. Potassium isn't in our list of exceptions, so it's soluble. Okay, now we need to turn the skeleton equation into a balanced equation. So I'm going, okay, we have 2 iodides coming out. We need 2 going in. And I need 2 potassiums going in, so I need 2 coming out. Bromides, there's 2 coming in and 2 coming out, so everything's balanced. All right, last but not least, sodium metal. So sodium metal reacts violently with water. So in this case here, so water, obviously it's H2O, but to make life easier, I'm going to write it slightly differently. There's still 2 hydrogens, still 1 oxygen. This is still water. Okay, but it just makes figuring out the products a bit easier. Okay, so you can think of water being made up of a hydrogen and a hydroxide. Remember, hydroxide is OH1-. Okay, so we're going to treat the hydrogen right here as the thing that likes to form the positive ion. Sodium also likes to form positive ions, the +1 ion. Okay, so positive switches with positive. So I'm going to get sodium hydroxide and water. I should put that state as liquid. And then we have hydrogen by itself, but remember Hofbrinkel, hydrogen is a diatomic element, so there's going to be 2 of them when it's by itself, and hydrogen is a gas when it's by itself at room temperature. Now, sodium hydroxide. Let's figure that out, what its solubility is. So hydroxide is right here, and it says group 1 ions. Sodium is a group 1 ion. How do I know that? Well, if I take a look at this, group 1 is right here. So it includes everything in this column here, which, guess what? Sodium is in the first column, so that's why it's a group 1 ion. So if I go back to our solubility table, it did say that hydroxide with anything from group 1, that is going to be very soluble, or in other words, it's aqueous. All right, and let's see. So right now we have a skeleton equation. We have 1 sodium coming in, 1 coming out. I'm still going to break up water and balancing it like hydrogen and hydroxide, just to make life easier because a polyatomic ion is involved. So we have 1 hydrogen coming in, 2 coming out. So what I'm going to do is I'm going to put a 2 right here. So now we have 2 hydrogens coming in, 2 coming out. We have 2 hydroxides coming in, but only 1 coming out. So I need a 2 right there. So hydrogen and hydroxides are balanced. Now we need to balance sodium because we have 1 coming in and 2 coming out. So I need a 2 right there. So now that's balanced. So again, reminder, make sure you do not forget to write your states because that is important. We're going to move on to double replacement reactions, which are similar enough to single replacement reactions. So they're going to run off of the same principle of positive ions switch with positive ions, or you could think of it as negative ions switch with negative ions. Essentially, for double replacement, you choose one and you stick with it, okay? All right, so double replacement is when 2 ionic compounds react to form 2 new ionic compounds. Okay, so you could kind of think of it like if there are 2 pairs of dancing partners and they just decide to switch 2 partners in between the 2 pairs. Okay, so that's essentially what's happening here. So for example, I'm going to color code this so it's a little bit easier to see. Purple will be the positive, or the ion that likes to have a positive charge, and blue will be the ion that likes to have a negative charge. Okay, so like I said, choose one, don't do both. Okay, so you could either think of it as positive switches with positive or negative switches with negative. The reason why I'm saying choose one, don't do both, is because if you switch both the positives as well as both the negatives, you're going to get the same products. Okay, so that's why I'm saying pick one, stick with it. I personally like to switch the positives, but if you like to switch the negatives, you will still get the same answer. So we'll switch positive with positive. So C goes with B and A goes to dance with D. There you go. So for example, we have gold 3 chloride. So gold is Au, has a 3+ charge. Chloride has a -1 charge. So we know 3 minus 1, that does not equal 0, so we got to do crisscross applesauce. So there, since it's a solution, it's aqueous. And we have ammonium iodate. So remember, ammonium, even though it's made up of all nonmetals, it acts like it's a metal. That's why we can still consider ammonium iodate as an ionic compound. And iodate, I gotta look that one up. Okay, so iodate is IO3. 1 minus. IO3. So since 1 minus 1, that's equal to 0, we do not need to do crisscross applesauce. And since I only have one of each polyatomic ion, I do not need to put brackets. Okay, if you're wondering how I knew ammonium was NH4, you can find ammonium right here. All right, so since it's a solution, that's also AQ. So they react together. Okay, we need to predict products. Okay, so again, I like to just consider it as positive switches out with positive. So gold is going to switch spots with ammonium. That's what's happening here. So ammonium, again, it likes to have that +1 charge. We have chloride, and the 3 doesn't stick around. The whole purpose of subscripts is just to balance the compound. Because chloride likes to have a -1 charge, this is already balanced. I will worry about the state later. Okay, gold is gonna be dancing with iodate here. So gold, we were told it has a 3+ charge. Iodate has a -1 charge. So we know 3 minus 1, that does not equal 0. We got to do crisscross applesauce. Because this 3 is going to go behind a polyatomic ion, we need to put brackets here. All right, that is balanced. Okay, now let's figure out what the states of these are. So we have ammonium chloride. Let's do that one first. Alright, so chloride, most things are soluble. Double check that ammonium isn't the list of exceptions. It's not, so that one's aqueous. Oh. Okay, and gold 3 iodate. Let's see. So iodate is right here. I'm not seeing gold here, so then it's going to fall under most. Slightly soluble just means you put it as a solid state. Okay, so now what we're going to do is we're going to turn the skeleton reaction into a balanced reaction. All right, so we have 1 gold coming in, 1 coming out. We have 3 chlorides coming in, 1 coming out, so I'm going to put a 3 right there. Okay, we have 1 ammonium coming in, 3 coming out, so I'm going to put a 3 right there. That 3 didn't just affect ammonium, it also affected iodate, and there's 3 iodates coming out, 3 going in, so everything is balanced now. So again, just for single replacement and double replacement reactions, I encourage students to treat polyatomic ions as one unit to make balancing easier. Okay, I don't recommend that for formation or decomposition or combustion reactions. All right, moving on. Sodium perchlorate. So sodium perchlorate, let's look that one up. So perchlorate is right here. Ooh. So it's Cl O4 1 minus. Okay, this likes to have a 1 minus charge. Sodium likes to have a +1 charge. That equals 0, already balanced. Because it's a solution, I'm writing AQ. Plus cesium phosphate. So phosphate likes to have a 3 minus charge. And cesium, by the way, if you were wondering where phosphate was, you can find phosphate right here. Okay, And cesium is going to be right here. It's a group 1 ion, likes to form 1+ ions. Okay, so we know 1 minus 3 does not equal 0, so we got to crisscross applesauce. And since the S is kind of looking like a 5, I will fix that. Cesium. So that's going to be a 3 right there, and that is balanced. Since it's a solution, it's AQ. Okay, I'm going to stick with positive switches with positive. So remember, this 3 is not going to come along for the ride. Okay, subscripts are only for balancing compounds. So we're going to get cesium, which has a 1+ charge, perchlorate, which has a -1 charge. So that's already balanced. I'll worry about the states later. And then we have sodium, which likes to have a +1 charge, phosphate, which likes to have a -3 charge. So 1 minus 3 is not 0. We got to do crisscross applesauce. So there we go, and that is now balanced. Now let's check solubility of both of these. Okay. So for cesium perchlorate, perchlorate is right here. Most things are going to be soluble with it. Let's just double check that cesium perchlorate isn't in our list of exceptions, because it actually is. So this is going to be solid. Okay, and then sodium phosphate. Let's find our anion first. So phosphate's right here, group 1 ion. Sodium is a group 1 ion because, as you can see, let me zoom out a little bit. So group 1, you can figure it out from the top, and sodium's right here in the first column, so that's why it's a group 1 ion. Okay, so what this means is that phosphate, when it's paired with a group 1 ion, it's going to be very soluble, so it's going to be aqueous. Alright, so now we have a skeleton equation. Let's balance the whole thing. We have 1 sodium coming in, 3 coming out. So let's put a 3 there. Okay, so now we got 3 sodiums coming in, 3 coming out. That 3 didn't just affect sodium, it also affected perchlorate, so I'm going to need to put a 3 there so that there's 3 perchlorates coming out. The 3 didn't just affect perchlorates, it also affected cesium. So we have 3 coming out, but guess what? We also have 3 coming in. So that's balanced. Phosphate, there's 1 phosphate coming in, 1 coming out. That's good. Everything's balanced. Okay, last but not least, barium hydroxide. So barium is a group 2 ion. So we got to do crisscross applesauce, put brackets around my polyatomic ion, and put a 2 right there. So it does say that this is a solution, so that's going to be aqueous, and it reacts with, so that's why I'm writing the plus sign, hydrochloric acid. So hydro, if it starts with hydro and ends in ic acid, it's hydrogen with only 1 other element. So because chlor kind of sounds like chlorine, I know it's HCl. And acids are always aqueous. All right. So with this, again, I'm just sticking to positive switches with positive. So barium switches with hydrogen. So I'm going to get HOH, which is just water, because it has 2 hydrogens and 1 oxygen, so H2O. So I'm going to put it as liquid. Water is never going to be aqueous. It's either going to be a liquid, a gas, or a solid. It is never aqueous. But in this case, because we are assuming this occurs at room temperature, that's why I'm putting water as liquid. Okay, and then we have barium chloride. Remember, barium likes to have a 2+ charge. Chloride likes to have a 1- charge. So crisscross applesauce. There we go. Okay, barium chloride. Let's figure out the state on that. So let's get rid of some of this stuff here. So chloride, most things are soluble. Let's just double check. Barium is not in our list of exceptions, therefore we are good to go. This is aqueous. Okay, let's clean this up. Okay, so we have a skeleton equation right now. We need to balance it. So we have 1 barium coming in, 1 coming out. 2 hydroxides, only 1 hydroxide. So we're going to treat water as hydrogen and hydroxide. So 2 hydroxides coming in, I need 2 going out. So there we go. Okay, hydrogen, 1 coming in, 2 going out. So I need 2 right here. But that 2 didn't just affect hydrogen, it also affected chlorides. So we have 2 chlorides going in and 2 coming out. That's balanced. All right, and that is done.